Section. Introduction. Let's dive into the world of natural language processing, NLP. The recent advancements in this field have been largely driven by the development of larger language models. These large language models, pre-trained on vast amounts of text, have proven to be effective in a variety of tasks. Interestingly, some studies have shown that these models can develop new abilities, like few-shot prompting and chain-of-thought reasoning, when they have a large enough number of parameters. Other research has focused on understanding how these large language models scale. They suggest that for optimal training, the size of the model and the amount of training data should increase at the same rate. This gives us a guideline on how to choose the model size and allocate the training data when we have a fixed compute budget. However, while there's a clear preference for large models, the potential of training smaller models with larger datasets is still not fully explored. This is where the concept of inference optimal language models comes in. These models aim for the best performance within specific inference constraints. They are trained with more data than what is typically recommended by the scaling law. Studies have shown that these smaller models, when trained with more data, can match or even surpass their larger counterparts. They also suggest that existing scaling laws may not accurately predict situations where smaller models are trained for longer periods. Inspired by these findings, we decided to explore how smaller models behave when trained with a significantly larger amount of data than what is suggested by the scaling law. We trained a transformer decoder-only model with 1.1 billion parameters using approximately 3 trillion tokens. As far as we know, this is the first attempt to train a model with 1 billion parameters using such a large amount of data. We named our model TinyLlama, following the same architecture and tokenizer as Llama 22. TinyLlama performed impressively, even when compared to existing open-source language models of similar sizes. Specifically, TinyLlama outperformed both OPT 1.3b and PyThia 1.4b in various tasks. We've made TinyLlama open source to improve accessibility for researchers in language model research. We believe its excellent performance and compact size make it an attractive platform for researchers and practitioners in this field. Now, let's talk about how we pre-trained TinyLlama. We used a mixture of natural language data and code data, sourced from SlimPajama and StarCoder data respectively. SlimPajama is a large open-source corpus created for training language models, while StarCoder data is a dataset collected to train StarCoder, a powerful open-source large code language model. After combining these two corpora, we had approximately 950 billion tokens for pre-training. TinyLlama was trained on these tokens for about 3 epochs. In terms of architecture, we followed a similar model to Llama 22. We used ROPE, rotary positional embedding, to inject positional information into our model, a method widely used by many large language models. We also applied RMS norm as our normalization technique for more stable training. Instead of using the traditional ReLU nonlinearity, we combined swish and gated linear unit together, referred to as SWIGLU, as our activation function in TinyLlama. Section summary. Recent progress in natural language processing, NLP, has been driven by scaling up language model sizes, with large language models, LLMs, demonstrating their effectiveness on various tasks. While previous studies focused on training compute optimal models, this work explores the behavior of smaller models trained with a significantly larger number of tokens, showing that smaller models, when trained with more data, can match or even outperform larger counterparts. The pre-training process of TinyLlama involves a mixture of natural language data from SlimPajama and code data from StarCoder data, with a similar architecture to Llama 22, ROPE for positional embedding, RMS norm for normalization, and SWIGLU as the activation function. Section. Grouped query attention. We've implemented a technique called grouped query attention in our model to minimize memory bandwidth overhead and accelerate the inference process. This involves using 32 heads for query attention and dividing them into 4 groups of key value heads. This allows the model to share key and value representations across multiple heads without significantly affecting performance. To speed up the training process, we've integrated fully sharded data parallel, FSDP, into our codebase. This allows us to efficiently use multi-GPU and multi-node setups, significantly improving the training speed and efficiency. We've also incorporated flash attention 2, an optimized attention mechanism, into our model. This, along with fused layer norm, fused cross-entropy loss, and fused rotary positional embedding, significantly enhances computational throughput. We've replaced the fused SWI-glue module from the Xformers repository with the original SWI-glue module, further improving the efficiency of our codebase. This allows us to reduce the memory footprint, enabling the 1.1 billion parameter model to fit within 40 GB of GPU RAM. These enhancements have increased our training throughput to 24,000 tokens per second per A140G GPU. Compared to other models like PyThia 1.0b and MPT 1.3b, our codebase offers superior training speed. For example, the TinyLlama 1.1b model requires only 3,456 A100 GPU hours for 300 billion tokens, compared to Pythia's 4,830 and MPT's 7,920 hours. This demonstrates the effectiveness of our optimizations and the potential for significant time and resource savings in large-scale model training. Our framework is built on LitGPT. We use an autoregressive language modeling objective during the pre-training phase, following the Llama 22 approach. We use the AtomW optimizer, with beta_1 set at 0.9 and beta_2 set at 0.95. We also use a cosine learning rate schedule, with a maximum learning rate of 0.0004 and a minimum learning rate of 0.00004. We use 2,000 warm-up steps to optimize learning, a batch size of 2 million tokens, a weight decay of 0.1, and a gradient clipping threshold of 1.0. We pre-train TinyLlama with 16 A140G GPUs. We evaluate TinyLlama on a variety of common-sense reasoning and problem-solving tasks and compare it with several existing open-source language models with similar model parameters. We primarily focus on language models with a decoder-only architecture, comprising approximately 1 billion parameters. Specifically, we compare TinyLlama with OPT 1.3b, PyThia 1.0b, and PyThia 1.4b. To assess the common-sense reasoning ability of TinyLlama, we consider tasks such as HelloSwag, OpenBookQA, Wino Grande, ArcEasy and ArcChallenge, BoolQ, and Pika. We use the Language Model Evaluation Harness framework to evaluate the models. The models are evaluated in a zero-shot setting on these tasks. TinyLlama outperforms the baseline models on many of these tasks and achieves the highest average scores. We also evaluate TinyLlama's problem-solving capabilities using the Instruct-Eval benchmark. This includes tasks like Massive Multitask Language Understanding, MMLU, Big Bench Hard, BBH, Discrete Reasoning over Paragraphs, DROP, and Human Eval. The models are evaluated in a 5-shot setting for MMLU, a 3-shot setting for BBH and DROP, and a 0-shot setting for Human Eval. TinyLlama demonstrates superior problem-solving skills compared to existing models.